So we can finish a couple of things that still all. I wish that we had more time, but that's fine. Yeah, what we saw last lecture. So basically, we saw that uniformization theorem implies that basically any compact genus G Riemann surface, any Riemann surface. Okay, so let me put compact Riemann surface with genus G bigger than or equal to 2 is a quotient of the upper half plane. Is a quotient of H. This is the upper half plane, which is a complex curve itself. By a discrete subgroup gamma, this discrete subgroup of the automorphism of upper half plane. We know this is PSL2 R, which is nothing but automorphism, complex automorphisms of upper half plane. So in a way, we see we know all these. In a sense, we know all these compact Riemann surfaces of genus G bigger than or equal to 2. And of course, G equal to 0, G equal to 1, you have to rely on the other two cases of uniformization theorem, but that's much easier than this one. Of course, gamma is isomorphic to pi1 of your Riemann surface. This is the of course, not all discrete quotients are compact, right? We should be aware of that. Not all quotients are compact. So I started discussing a special case, which was if we take gamma to be PSL to Z, which is unimodular integral matrices with determinant divided by the center, this one, then H divided by PSL to Z by this discrete subgroup, it's something that's called modular curve. Actually, its proper name is elliptic modular curve. It's elliptic modular curve. And you can see it roughly like this. So idea of proof. There are two generators for PSL2 Z. Generators of PSL2 Z. There is this generator T, which is the translation by 1. You're shifting across the x-axis by 1. T of Z equal to, you see, all these guys are acting by Mobius transformation. So one of them is Z plus 1. And the other one is minus 1 over Z, deflection through the unit circle. The other one is S, usually denoted by S. The other one is S of Z equal to -1 over Z. Okay. So when you look at these two things, then you can find a fundamental domain for the action. A fundamental domain. There are many fundamental domains for the action, but a fundamental domain for the action. So it's the following famous construction. So what you do, you can just first of all, you know that because of these translations, it's enough to focus on one strip of length 1, like this. Of course, this line is the line at infinity, is the boundary. So this is not part of the story. So we just also dash this. So this is half. This is minus half. So just purely using t, you can make everything outside of this strip congruent to something inside. So you can make it almost uniquely, except if these points and that point they have the same representative. They get identified under the quotient, but that's okay. But then, so what you do, you have to also use this because you don't need all of this strip. You need just the strip that is like this. I mean, this needs a proof, but that's not too bad. So there is a circle of radius 1. Oh, that's too bad. Okay. Okay. Right. So then what you have all the way up, and this up, and this one. Okay. You can show that, for example, this again is congruent to this one. By S comes here. We don't need this. We just focus on this one. So let me put this circle so that we can see the circle. This is the point I, and this point, it has coordinate 1/2 plus I root 3 over 2, and this point has coordinate minus 1/2 plus I root 3 over 2, right? And obviously this line, this piece of circle, gets identified with this piece of circle on the left, because you have S that maps this to that. And also this line gets identified to that line. So after identification, you do get a non-compact Riemann surface, which I called it M. I don't know if I have the notation introduced or not. So this is M, the non-compact Riemann surface. So it's just called the modular curve. And so now you have to think of this after identification. So one way to think of this is like this. So there is a point at infinity here. This is called the cost point. And there is these 2 points get identified, and I is a special case because these are fixed points. So there is one point which is I here, and the other 2 points get identified. So there is this point. So these are the special points. The Riemann's the surface is smooth. There's no singularity. No, there's nothing funny going on. It's a little bit counterintuitive because you may think that because this point actually has a fixed point of order 3. There's a cyclic group of order 3 that fixes this point, and there's a group of order 2 that fixes this point, but that's okay. In the complex case, this fixed point don't cause any problem in the holomorphic category. Okay, now this is non-compact. And topologically, obviously, is isomorphic. Topologically, it's homeomorphic to C, right? So the question is, can you write a biholomorphism between this and C? That's what we want to look at, right? So, any questions about this? Okay, so the question is, there exists. I mean, we know by abstract reasoning there should exist because any Riemann surface like that is simply connected and is non-compact, so it has to be C or upper half plane, but it's not upper half plane actually. So this we can, I mean, I'll just write it down now. There exists a biholomorphism from this modular curve M, which is H divided by PSL to C, Z to C. So this is actually induced by a map J, which goes from the upper half plane to C. It's holomorphic and PSL to Z invariant. It is holomorphic and PSL to Z invariant. In the sense that J of gamma Z is equal to J of Z. There is no automorphic factor or there is no quasi-periodicity. There is on the nose periodicity, which is J of gamma Z equal to J of Z. This is for all Z belonging to H, and for all gamma belonging to PSL to Z. A holomorphic map. Because if you, I mean, existence of this map is exactly equivalent to existence of this map because, you know, these are the invariants. It goes to the quotient of something in the quotient, comes from upstairs, which has to be invariant like that. So the question is, what is this map? So this map J is a very important invariant of I should say complex analysis and arithmetic. This J is called the fifth operation of arithmetic. It's the fifth operation. We all know the other four operations, right? Of arithmetic. The other fours are addition, subtraction, multiplication, and division. That's what we learn in elementary school. So J, unfortunately, we have to wait for a little bit more adult age to be told what it is. So this is what classics told us. J is the fifth operation of arithmetic. So let me write this J. This is constructed. This is a very important object in modular forms and complex analysis, Riemann surface theory, everything. So this is constructed like this. It's good you see that because it's, so I just erase this part. So J of tau, or tau, now I just switch, so maybe I call this tau. For the upper half plane, we always denote it by tau, yeah, okay. Yeah, okay, so J of tau equal to 1728. Yes, 1728 times G2 tau cubed over G2 tau cubed minus 27 G3 tau squared. G3 tau squared. Where you see, we met these guys before. These are Eisenstein series where G2 tau, we saw it in capital G and little g as well. G2 tau is 60 times some gamma to the power minus 4 Well, gamma belonging to gamma, and gamma is different from 0. So we just sum over non-zero elements in the lattice, and G3 tau is equal to 140. So it's a weight 6. Yeah, modular form, in fact. Gamma belonging to gamma, this is gamma to the power -6. And this is gamma. I mean, SL2Z is gamma, yeah. This gamma is SL2Z that we always found, PSL2Z, doesn't matter. So, yeah, you see, this guy is not invariant. This guy is also not invariant. But when you divide, you see, they have the same degree in the numerator and denominator. When you divide, you do get an invariant thing. And this invariant is holomorphic, is never zero, is the most beautiful object you can imagine. There is no singularity, nothing, and gives you an isomorphism by holomorphism between this and the upper half and C. Okay, so J, okay, I wrote it here. J is a biholomorphism. No. J goes from here to there, but on the quotient, because of on the quotient, it gives us isomorphism between this and C. I think you can actually directly prove that this cannot be upper half plane. I mean, I don't see the proof right now. This, I think, can be rejected. So, I mean, but to show that actually explicitly, you know that there should be a map to show that explicitly this upper half planes. So this is example one non-compact thing. Although it's non-compact, but it has a finite area, this thing. So that's another nice calculation I want to show you. Any question about this? This guy, this thing, modular cap has finite area. So let me show you. So this is the modular curve before identification. Okay, so before identification, so claim is that modular curve has finite area. Although it's non-compact, but it has finite area. I mean, but area under so area form. This is obtained but there's a Riemannian metric obtained from Poincare metric. On H, which is this metric ds squared. It's a Riemannian metric equal to dx squared plus dy squared over y squared. This is the metric that gives us, this geodesics gives us non-Euclidean geometry, the famous non-Euclidean geometry, which was all the rage in 19th century. Everybody wanted to know what it is. Non-Euclidean geometry metric. So, or you can say hyperbolic geometry, same thing. Hyperbolic geometry metric. And so then from here, you can construct the area form, which is, it turns out to be dx dy over y squared. That's the area form. Okay. So the question now is if this integral over this area d, now this is the calculus integral, really dx dy over y2 is less than infinity or not. This is the question. Because that's the area, and that's the invariant, this area form is invariant under the action of things. Now, well, this is elementary to see that this is finite. You can see that, right? Because this you can integrate from -1 to -half to half is constant. So the x integration, there's no x here, so x integration drops out. and the y integration. So this follows from the fact that the integral from 1 to infinity, for example, dy over y2 is less than infinity. So this implies. So this is a finite area. Now I mentioned this metric, so I'm sure you have seen it in hyperbolic geometry, non-Euclidean geometry. What are the geodesics of this, right? So the geodesics of this. So I won't discuss that, but one thing I want to tell you, that's in relation to the group of automorphisms of the upper half plane, which is going to be exactly a group of isometries of this metric. They are the same up to orientation. So note that actually PSL2R, which is exactly, did I write PSL2Z is automorphisms of H? Did I write that? No, I wrote inside I wrote inside automorphisms of H. Yeah, yeah. This is the automorphisms of H. It's exactly PSL2R. This is exactly automorphisms of H. But that's exactly group of orientation preserving isometries of this, Poincare metric. Of course, you can always go to orientation reversing by multiplying everything by one orientation reversing thing. So it gives a doubling, but if you stick to orientation preserving, this is exactly. So this is a relation between Riemannian geometry and complex geometry in this picture. Okay. Any questions? Kobe, is everything okay? I didn't make any, I don't have any typos there. Great. Yes.
You drew another diagram.
Sorry?
You drew another diagram like that, where you had I as well as.
This is I here.
Right.
And these are these 2 points, yes.
Right. And then you drew another diagram where I and the 2 points are identical, right?
Yes, that was after the identification, yeah.
Okay. What's the relationship between this diagram?
Well, this is the quotient of this by this action of Z, by action of S and T. If you
translation and the 1 over Z.
Yes, minus 1 over Z.
Minus 1.
Because if you do 1 over Z, you're thrown out of your space. You have to do minus 1 over Z to stay in the same space.
So that I will map
I is a fixed point, as well as these 2 points. Actually, I is the fixed point of S. S is something has order 2. But these 2 points, the element is, I believe, is ST, which has order 3. So it's a cyclic group of order 3. So a stabilizer, these 2 points, a cyclic group of order 3, but this point is a cyclic group of order 2. Yeah. Is that what you wanted?
Yeah.
Okay. Now, let me give you one more example of this, which at least maybe you can see a little more. So I told you how to construct lots of interesting discrete subgroups. Of course, there are many ways. I mean, Poincare already started a very deep analysis of these discrete subgroups of PSL2R. I think he could construct them all by geometric means. But so more discrete subgroups. I mean, these are important, I think, maybe for modular forms and number theory, but they are also important, yeah, for other things. More discrete subgroups of PSL2R. So I believe I started discussing this. So I said fix n bigger than or equal to 2, an integer, and consider this map Z to the nz. So this quotient map, this is a ring map, which is a ring map. So this induces a map between corresponding groups, PSL2Z to PSL2Z over NZ. Of course, this is a finite group. This finite group, and I call this map pi maybe. And then there is a subgroup. It's called X. It's called gamma n. By definition, is just the kernel of this map. It's a normal subgroup. Kernel of pi. It's a normal subgroup, which you can say is the set of all ABCDs, such that A equal to D equal to, so A equal to D is equal to, is congruent to 1. So A is congruent to 1 mod n. D is congruent to 1 mod n. I think 1 is enough. 2 is enough. And B and C are congruent to 0 mod n, obviously. Okay, so now, so in this case, this level n modular curve. Again, these Riemann surfaces, some of them are compact, some are not compact. So deciding which is compact, which is not compact, and when it is compact, what's the genus of this, it's a huge industry. But I'll give you a couple of examples about these things now so that you have a feeling. I give you one compact example, one non-compact example. So level n modular curve. This is the Riemann surface. Okay, so historically, there is a first case which was studied by Klein, actually. Yeah. Felix Klein. I believe he maybe took it up around the 1880s, most probably around that time. So he took n equal to 7, famously. And he looked at x7. Then he really studied this case in detail, what happens. For example, he shows that this x7 has a famous name. It's called Klein quartic. He showed that this admits an embedding into projective plane. Embedding, because I mean, this is abstractly defined as a quotient of upper half space, but you can embed it into P2 actually, not P3. P3 is not needed even. Embedding into projective plane P2C. And he showed that the image of this has the equation so there is one equation which is I think perhaps I don't know. So this equation, maybe you have seen it. So this equation is x3 y. I have to want to write something which is not right. Oh yeah, x3y plus I mean we just go on. Like y3 is a cyclic thing plus y3 z plus z3 x equal to 0. So that's the projective equation for this. And a nice exercise, simple, but it's good to do it, is to show that actually this is a smooth. This is a smooth projective curve. So in particular, this x of n is compact. Then he knew that it has genus 3. x7 or x7, sorry, units of x7 is equal to 3. He did a lot of work on this, but another thing is he calculated, I believe, the automorphism group of these biholomorphisms. And he showed that actually the order of the automorphism groups of X7 is 168. Yeah. So you may wonder, so what? So let me tell you why. Because there is a theorem of Hurwitz, which we did not get a chance to discuss, but there's a famous theorem of Hurwitz. I think Hurwitz was proved after this because actually, you know what? This curve, this Riemann surface, they say, is the first Riemann surface that was studied by mankind explicitly. So an explicit Riemann surface that, I mean, Riemann did all these amazing things, but in terms of explicit examples, I don't know. So this has a very important historical relevance. Anyhow, so Hurwitz's theorem is the following. It's quite surprising. For genus bigger than or equal to 2, the automorphism group of these compact Riemann surfaces is finite. Order of automorphism groups of X is actually less than or equal to 84 times G minus 1. Yeah. This is called Hurwitz bound. This is not so bad. You can prove using Riemann rock and little work, some smart work is needed, but it's not so bad, but don't have time to get into that.
Professor, is it a coincidence that the equality happens here? When does the equality happen?
No, so the fact that equality happens, it means that they are maximally symmetric. They are the most symmetric thing. So for most cases, it doesn't happen, but this happens. I mean, it's also a reflection of this nature of this equation. You see, this equation is so symmetric. If you introduce some coefficients, you still get the smooth, smooth curves, but the automorphism group is violated. It's not going to be these, but this is very, very symmetric. I mean, G, of course, in this case is equal to 3. So this is 168. I mean, this is, I mean, this is exactly equal to that. So yeah, so I don't know if I believe there are nice pictures in Wikipedia for places for Riemann, for Klein quartic. So this is a compact example, and there is also a non-compact example. I could tell you, but maybe I avoid that because that involves again writing more modular form. In this case, theta functions. So I think I will stop writing that. Okay. Okay, so yeah, so you have seen some examples. So any question? Okay, so now I will go back to discussions of this Abel Jacobian, and we'll visit some interesting aspects of Riemann surfaces, which still we have to discuss. So back to, okay, so Jacobian. Of Riemann surfaces. So you remember for a compact Riemann surface X, we define Jacobian of X, right? By definition, this is to be omega X star divided by this lattice gamma, where gamma is equal to image of H1 xz, the singular homology group, under the map P, the period map, which goes from H1 of xz to no, that's fine. That's fine. Into omega x star. So what is this map? Well, P of class of C is equal to the map that sends this holomorphic one form omega into integral of omega over C. This is just integration to be computed. Yeah, I mean, we saw that this gamma is a lattice of rank 2G. So in particular, this guy is an abelian variety. This omega Jacobian of x is an abelian variety. So let me define an abelian variety in general, because you want to see that this is a very special kind of a special kind. I will tell you exactly what is the special kind. So in general, an abelian variety is a compact, complex Lie group of complex dimension, some G. I mean, this, as I told you several times, this Lie group has to be abelian because of this. In the holomorphic category, you cannot have compact non-abelian group structures. So let me put abelian variety is a compact Lie group A, okay, of complex dimension, G bigger than or equal to 1, and yeah, okay, so right, of the form, so it turns out that it is necessarily of the form. You can prove that it's not difficult. It's necessarily of the form. You can show that A actually is always going to be V divided by gamma, where V is a complex vector space of dimension D. And gamma subset of V is just a discrete rank 2 lattice, discrete rank 2G. 2G lattice.
So does every abelian variety arise from a Jacobian?
Sorry?
Does every abelian variety arise from Jacobian?
No. That's what I'm going to get at. No, not all abelian varieties are Jacobians. In fact, we don't even know if all polarized, principally polarized abelian varieties are Jacobians. We don't know that either. So let me define the thing that I have in mind, and then you'll see that, well, we can't prove, well, nobody knows, but okay, so let me tell you what it is. So there is an extra structure on Jacobian, which is called principal polarization. So this is extra structure on Jacobian of X. It is called a principal polarization. So So principal polarization, it's an inner, so, okay, so I define it for general abelian varieties, what is a principal polarization, and you see that why on Jacobians we have that. So on V, a principal polarization means that there exists a Hermitian inner product, positive definite inner product. Hermitian inner product. Hermitian product. But it is such that it takes integral values on the lattice. The inner product is integer on the lattice. And V1, V2 belongs to Z for any V1, V2 belonging to gamma. So this is called the principal polarization. Okay? So the Jacobians have this structure. We showed that. Jacobians, Jac X have this structure. You see, this why they have this structure? Because in the case of Jacobians, V is omega of X star, is the dual of differential forms, holomorphic differential forms. V is omega X star. And in that case, we can define this, I defined and I used this pairing, intersection pairing on one forms, which was omega 1. So let me put it like this, omega eta is equal to integral over your Riemann surface, omega wedge eta bar. So this is the Hermitian structure, but then we saw that if you introduce those singular homology bases over those, this actually takes integer values. Okay, I mean, we went a little bit the other direction, but that's and it is integral restricted to gamma, which is image of x1 h1, I mean x and z, right? So Jacobians are principally polarized, definitely. And the Schottky problem is that, is it true that any principally polarized Jacobian variety, the Jacobian of a curve, or not? So this we don't know. That's open. But there is something that's very interesting to know, and there's a theorem that actually tells you that Jacobians and its principal polarization determines the Riemann surface. So this is one aspect of Jacobian which shows its importance. So this is Torrelli's theorem. It's a famous theorem.
But the Jacobian alone doesn't determine.
Sorry?
Jacobian alone doesn't determine the.
No. Jacobian and polarization. So this is Torrelli's theorem. Basically, it says that if two Riemann surfaces are such that Jacobian of x1 is isomorphic to Jacobian of x2, and this isomorphism should preserve the principal polarization. So they should send principal polarization to each other, preserving polarizations. And then basically x1 is isomorphic to x2 as Riemann surfaces. I mean, so I will expand a little more. I mean, this is quite a strong result. I mean that. So basically, what it means that this Jacobian is a linearization of Riemann surface. So you have this very complicated object, which is a Riemann surface, because complex structures are very complicated. But this abelian variety linearizes this. It's really a torus with this complex structure, with the polarization, but still It's a little bit like going from Lie groups to Lie algebras, a little bit, not quite, but a little bit has that flavor. It's a linearization. Now, so what people do, they use this. Okay, now let me, maybe Megan will mention this in her talk. So I just want to give a little bit of introduction to what you just one sentence, not more than that.
I'll allow it.
I won't give any spoilers. I will be very okay. So for basically for any G, so let me take this case. So Mg, this is so you can think of Mg as moduli space of compact genus G Riemann surfaces, as you know. So modular space. So I'll tell you, I will give you a rough idea of this. This is not difficult. Modular space of compact genus G Riemann surfaces. Basically, this is the set of all compact genus G Riemann surfaces up to isomorphism. So this is a very, very rough, without giving any complex structure, any variety structure, anything. This is the coarse moduli space that we are considering. There is a lot of structure you can put on that. It's a complex manifold. So you can show that actually dimension of Mg over C is 3G minus 3. This is due to Riemann. Already in 1857, he wrote this formula. He gave some very sketchy arguments. It's an amazing observation of him. So you can also look at Ag, which is the, now this is much better, I believe. This is moduli space of abelian varieties of dimension G, complex dimension equal to G. And so this Torrelli theorem says that there exists an injective map from Mg to Ag. And this is called the Torrelli map. Okay. Now, dimension of Ag is also known. It's much bigger than this. Dimension of Ag is, that moduli space dimension is, I believe, G times G minus 1 divided by 2. It grows quadratically in G. So it goes much faster than this one. This grows linearly in G, but this grows quadratically in G. I believe this is correct, but okay, I may be off by a factor of 2 or 4 or something. Okay, so then this is one way to study modular spaces. You embed them into this, which is a little better. So this Torrelli theorem is yeah, when was it proved? In 1913. And yeah. Okay. Any question?
Can you give me an example of a abelian variety that is not a Jacobian?
Yeah, not now. That's a good question. Yeah. Yeah.
There are whole
Not.
papers.
Huh?
I think there are whole papers where someone just finds one. So.
Oh, is that right?
Yeah.
Oh, who's the author?
I don't know actually, but I've definitely seen.
Ask chat. They'll give you an example right away.
How about if you have two different Riemann surfaces with the same Jacobian?
Well, you mean the
Examples.
same Jacobian?
Yeah, you said the Jacobian alone doesn't determine the Riemann surface.
Yeah. Yeah, we need principal polarizations. Yeah. So you mean to have this same but different principal polarizations? Is that what you said?
Yeah.
Yeah. Yeah, I believe that's not difficult because this has to do with the structure of this period map, and period map is so sensitive to complex structure. So I think you take two algebraic curves with same structure and perturb coefficients a little bit, most probably you're going to get
Okay.
You're going, but okay, I mean, I don't commit myself to something explicit. Yeah. Okay, so now there is this, okay, so this is a little bit extra that would be good to know in this case. And we define then this Abel's map, because I promised to do something. So now this time we go back to Abel's map. So what is this Abel's map? So this A, I'm choosing now I'm changing the notation. A goes from X to Jacobian of X, which is again omega X star divided by this lattice, by the period lattice. Okay, so this is period lattice. To define this, we fixed, I already defined it 3 lectures ago, fix a point P of P0 in X. Then you just send P, to the following object in here, which is just the map that sends differential form omega through its period. From P0 to P. Yes. I mean, the class of this guy. So let me just maybe give you some indication of how it is. We fix a point P0 here, and then for any P, just take any curve, gamma. So the integration is over any curve. That doesn't matter. Over any curve. I mean, again, this doesn't matter because we are going into the quotient. We are dividing by this. You see, if you take another curve, for example, like this, okay? So the difference between these two values is integration along one loop, along one loop, and these loops are taken care of by these guys. We are dividing by this gamma. So that completely kills the ambiguity, and as a class, this is completely well defined. And okay, so this is the map. All right. So because now this is a abelian group, this guy here is an abelian group. So this A can be extended to a map from abelian group generated by X, namely the divisors of X, to this Jacobian X. And this map is just sending, so A of sigma NP P is equal to sigma NP A of P. This linearly extends the thing, right? P belongs to X. So I promised to prove Abel's theorem, which is a famous, very important theorem actually in this regard. So which is the following now. So let us restrict now A to div 0 of X, which is inside. So this is degree 0 divisors. 0 divisors. Okay. So these are divisors that the sum of NPs is equal to 0 in this picture of the divisor. So let's call this A0. A0 from degree 0 divisors to Jacobian of X. Okay, now the first thing which is very simple to see is that this map A0 now is independent of P0. That's so exercise. Actually, this is quite easy, but not bad to do. A0 is independent of the choice of P0, initial point. The choice of P0. So this certainly we can, you can easily show. Then the Abel's theorem is the following. Right, so Abel's theorem. D belonging to div0 of X. So let D belong to div0 of X. D is a principal divisor. Principal divisor. If and only if D belongs to kernel of this Abel's map. So you see we had the following picture. We had principal divisors inside degree 0 divisors. And this was inside all divisors. So we have this A0 here into Jack X. Now we want to see when something is in the kernel. The kernel is exactly principal divisors. You remember the principal divisors, right? What was the principal divisor? It's the divisor of a function, meromorphic, non-constant meromorphic function, right? So, okay, so I need 5-10 minutes. Just I will give the necessity of this. I will prove the necessity, and the existence is a little more involved, but exactly what we have, it's completely within reach. So let me give the proof in the case of necessity. Okay, so here, by the way, I mean, the fact that this is surjective is due to Jacobi. So this is called surjectivity of the map is due to Jacobi. So then, as a result, this divisor divided by principal, degree 0 divisors divided by principal divisors is actually the Jacobian of the curves. You see, it has a completely, I mean, how to say this? Elementary description after all these things, then you can completely describe it in terms of divisors and functions. That's it. I mean, okay. So let me now give the proof in the case of Abel's theorem, necessity proof. In other words, I want to, what I'm trying to say, I want to, no, is this sufficiency? So let me, so first we prove if D belonging is equal to divisor of an F non-constant meromorphic function on X, then D then D belongs to kernel of Abel's map. So this is 1/2. This is the easier half of Abel's theorem. The other part is existence part, which you construct really this function knowing that D is in the kernel, and that's. But I proved everything that we need because there's this bilogarithmic functions that you construct using Riemann rock. So I showed you how. Sorry. Oh, A naught, absolutely, yes. In my notation, I use A naught. Very good. Okay, so now, so how to prove it? So let D be equal to degree of F. So it has, so F goes from X to C hat, right? I mean, I just use F, I don't use capital F, that's okay. Let S be equal to set of branch points of this F. Set of branch points of F. So to get the so the notation now I used. So let me make sure I use the notation. Okay. So yes. Fix again as usual P0 belonging to X. So define a map. I believe I used the notation. Actually, I didn't use any notation. I just used from C hat, from the Riemann sphere, take away the branch points to Jacobian of X. Yes. That sends the point Q to the Abel map of the following things. The Abel map of the following divisor, sigma, I mean A0 of sigma I from 1 to n pi minus P0. Where what? P1, Pn belongs to F inverse of Q. You see, Q is here. It's not a branch point, right? So if you look at, so the map is not ramified on Q. So if you look at F inverse of this Q, it has n points where, what is the degree I chose? Oh, D. Okay, so let's call it n. Yeah. Right? So you're going, you know, from your surface here to Riemann sphere, but then we exactly deleted those branch points. But for any point Q out of branch points, the inverse image is exactly n points. So we call those points pi, and you just send Q to this point in the Jacobian. Okay. Just send it. Okay. I mean, this map is obviously holomorphic. I mean, this is because A is holomorphic map and here it's just holomorphic. It's also well defined because it's symmetric in PIs and it doesn't matter which order you choose here. So this map is holomorphic.
Anyway, define the theta.
For me,
F inverse, you have P1 through Pn in F inverse theta.
F inverse of Q.
Q. Oh, okay.
Yeah. The point I choose is Q. Okay, so we have defined a map for any point away from the branch points. Map is holomorphic on C hat. Take away the branch points, which is, I denoted the branch points by S. Okay. Then you can show it's not difficult actually. You can show that this map is actually continuous at those branch points. I mean, I don't know. I don't want to give names to these maps, but maybe I should. So let's call it H. H is actually continuous on C hat. Hence is holomorphic. Because you have a function which is holomorphic away from finite number of points and it's continuous at those points. And we know that for holomorphic functions, if there's the limit exists at the singularity, then that's actually holomorphic at the singularity. There are no funny singularities in complex analysis. Hence is holomorphic on C hat. Okay, so now the upshot is the following. So you get a holomorphic map from C hat to Jacobian. Which is omega of x star divided by gamma, but this is c to power g divided by gamma. Let's not forget that. Okay, then, but this guy is simply connected, right? C hat. So there's a little bit of topological argument now, but C hat is simply connected. I mean, pi 1 of C hat is 0. Of course, you know that, or 1 if you want, I don't know how you think about pi 1. So it means that then it admits a lifting to CG. Hence, H can be lifted. Because H you see goes from C hat, from a sphere to the quotient, but it can be lifted to the total space. It can be lifted to C power G. This is a flat complex vector space now. So, okay, so I call this map H hat or H tilde, which goes from C hat to CG. But then each component is holomorphic. What can we say now? Each component is holomorphic, of course, because it's a holomorphic in CG, and C hat is compact. So it's a holomorphic function on a compact space, so it has to be constant. Okay. And since C hat is compact, it immediately follows that H tilde is constant. Okay, now here is the beauty of this thing. Now, if point 0 and point infinity are not among the branch points, I mean, okay, so actually, let me not write it. Let me put it this way. So H is constant. Now, the fact that I didn't need that. The fact that H of 0 is equal to H of infinity, this exactly implies that degree, I mean, it implies that this divisor, so what we wanted to prove? We wanted to prove that this guy goes to 0, implies that A of D is equal to 0. So I leave that to you, think about it. This is not difficult, actually. It's a straightforward.
A naught.
A naught, yes. Thank you. It's A naught. Because you know the degree. I mean, this means degree of this guy, because degree really is about 0 at infinity. It's either zeros or poles. So that's okay. So yeah. I don't want to take more time now. So this is the easier part of Abel's theorem. So the second part, which is the converse, I mean, is a bit more involved, but Yeah, okay, so I don't want to. So, okay, I think for now we are okay. So now it's good to think, okay, so what is the application of Abel's theorem and what you can do with it? Immediately, what you can prove, the corollary of Abel's theorem is the following now. Okay, the Abel and Jacobi's theorem. The corollary is the following. Any Riemann surface of genus G of genus 1 is a torus, is a complex torus. C divided by Z, dx sum tau Z. Imagine part of tau in the upper half plane. I mean, this is the first time we could prove this because there was no other way. We proved the genus 0 case immediately after we did Riemann rock, but for this we need a little more information. So this basically implies that the modular space of genus 1 Riemann surfaces is essentially one-dimensional. It's actually modular curve, we know. I mean, this is really isomorphic to M, a modular curve that we study, but that needs a little bit of more argument. But immediately from this, at least you know that they're all parameterized by the upper half plane, point up to some equivalence relation, which is the modular. So this is something that, okay, so okay, I think I want to stop now. Do you have any questions or?